If every molecule had a different set of symmetry elements and operations, this would basically make life a bit more complicated because we'd have to deal with each molecule uniquely. But it turns out that many molecules have the same set of symmetry elements or symmetry operations, and we can gather those together in sets and understand that the symmetry properties of those molecules that share the same set actually will be similar themselves. So what we do is we define something called the point group. And the point group is basically the set of symmetry operations that belong to a given object or molecule. And this set of symmetry operations, then we know that that's going to be totally equal to the order H. So this, in some sense, sets a size scale to this point group. All right, now there are many different point groups, but it turns out there's only a small finite number that really impact our study of molecules very much. And so let me introduce you to some of those point groups. And what I want to do is tell you the labels that we use to denote those point groups, what some of the key symmetry elements there are in there, an idea of what their order is, and we can talk in another video about how one would actually go about identifying the point group that belongs to a certain molecule. So let's start with perhaps one of the most straightforward ones, and that is the CNV sets of point groups, where n is some number. Typically, n is equal to 2, 3, 4, 5, or 6. In fact, that will be generally true when we talk about these point groups. All right, a CN point group is one that contains a CN axis, and it will contain n different C sigma V planes. And so all of these are ones that contain that CN axis and are vertical planes in the molecule. All right, the total number of operations that this point group would have, so I'll make a separate listing over here to the side, the order of this would be equal to 2 times n. So if n is 2, then there'd be 4 symmetry elements or symmetry operations associated with that point group. All right, we can also have point groups with the symmetry operation, the designation of C2 of CNH. I'm going to focus in particular on C2H. That's the one that is most commonly encountered, and the others are perhaps less observed. In the case of a C2H point group, what we're going to find is that it has a C2 axis. It has a point of inversion symmetry, and it has a sigma H plane. All right, and along with the identity operator, this means it has a total of 4 symmetry operations, so its order would be 4. All right, we can have also symmetry groups, point groups, that have designations that use the label D. And the D and H are probably the most common ones that you'll run across. These contain the following symmetry elements. They would have a CN axis. They'll have a total of n different C2 axes. These will all be perpendicular to the CN axis. If n happens to be even, these will also have a point of inversion symmetry. If n is odd, it will not have inversion symmetry. We'll also have an improper rotation axis, and this occurs because these molecules, this point group also has a sigma H plane. Now again, if n is even, we'll have n over 2 different sigma V planes, and we'll have n over 2 sigma D planes associated with these systems. All right, so the total number of symmetry operations, the order of these point groups, will end up being 4 times the number n, and that will be true whether it is n is even or odd. All right, we can also have symmetry groups, point groups, with the designation D sub ND. All right, so you might guess that it's going to have some sort of dihedral planes associated in this one. All right, in these particular point groups, again, we have a CN axis. So you'll see there's a common thread running through here, that we have a CN axis in all of these as the principal axis of rotation. So looking for that is a key way to begin to identify these point groups. These will also have an S2N improper rotation axis. It will contain N different dihedral reflection planes and N different C2 axes. All right, so quite a bit going on there. These particular point groups will again have a total order that corresponds to 4 times N. Now, in addition to these are the ones that you're going to find describe many of the molecules that contain symmetry that we'll be looking at. However, there are some other special categories, and I'll actually denote them as special categories that we should be aware of. Okay, first of all, what if the molecule is linear? Okay, in the case of a linear molecule, there are only 2 possible point groups that this molecule could have. Those 2 possible point groups correspond to the following. They could be sigma infinity V, C infinity V, or D infinity H. What's the difference between these? Well, D infinity H is if the molecule happens to be symmetric. So, for example, this would apply to something like carbon dioxide. It's a linear molecule, but it's symmetric, so we can flip it around and get the same thing back. C infinity V would correspond to a linear molecule that's not symmetric. So, for example, hydrogen cyanide would be a good example of a C infinity V molecule. So these are molecules that actually have an infinite order because they have an infinite number of planes that can contain the axis along which the molecule lies. All right, infinite number as we rotate around this internuclear axis. All right. So in this case, perhaps the order is not so much something that helps us out a lot. All right, there's also a special category for groups that I'll call cubic groups. And I won't go through a whole litany of the different elements that they have, but there are 2 particular types. There are tetrahedral types that we find in common, and these include the point groups T, TD, and TH. And TD is one that you're most likely to see. It would include things like methane, which has a tetrahedral arrangement of its bonds. Something like that. All right, these have very high orders of operations because they have a lot of symmetry elements. So, for example, the T group has 12 symmetry elements. TD and TH both have 24. So quite a few elements associated with these. We can also have cubic groups that are based on octahedral symmetry. So these are going to be particularly important with transition metal complexes, for example. And again, this will come in more than one variety. We can have O or we can have OH. This octahedral one is the one that you'll find more common with the octahedral complexes. And these have also a lot of different symmetry elements. The O group has 24 symmetry elements, while the OH has 48. So a huge number of symmetry elements. I should mention that there are a couple of other point group designations that you may run across. In fact, they're also pretty common. One of them is C1, which means there are no symmetry elements. The only element that this one has is E. There is CS, which has a very limited number of symmetry elements. It's typically planar molecules with no other symmetry. So these will have a sigma H plane and an E, but very little else. All right, so this gives you an idea at least of the general rundown of point groups. You'll see several examples of this, and you'll see certainly several examples of the ones given here. And you should look in the Symmetry at Otterbein website for even more information about all of these.